Uh, Good evening, everyone. Myself Suresh Kanodia. I am in Geoscience department. So in this lecture, we will discuss about the how space and ground-based observation can be useful to study the crustal deformation in and around India as well as around the world. So we all know that when we talk about the geodynamics, so it starts from the formation of the Earth, then followed by the internal and near surface structure of the Earth, and the plate movement, then the consequences of the plate movement. So we know that there are various formation of faults, fold, okay, then followed by so many minerals deposit, so many then resourceful geological formations, crude oil, minerals, then some other things. So to study all these geological features, we need a technology. Then only we can efficiently, because in geology we only the studying the surface of the earth, but we are not going in the subsurface. So here, when we want to have this subsurface information like subsurface lateral variation, vertical variation, so we need a ground-based observation, because surface is giving the this space-based satellites. It's giving only the surface information, not the subsurface information, except few satellites like GRACE. It's giving the basically the gravity anomaly, but it's related to subsurface phenomena like magnetometer. So there was so many this magnetometer mission, so it is giving the subsurface phenomena, but it is also a recurrence information only, because when we want to confirm this, we have to invert the data. Basically we have to invert means we have to do the inversion, we have to do the forward modeling, inverse modeling, then we can quantify, and then we can give the some concrete information about the presence of geological features, our phenomena. So here I will discuss only about the crustal deformation. So in this here you can see that if you see the northwest Himalaya, basically in the Indian part, Indian administrative boundary part, so you can see the numerous fault, okay, numerous major fault, active tectonic fault, neotectonic fault, and then you can see the concentration of the seismicity. So in this here you can see the seismicity since 1900 to present, that how the seismicity is concentrated in and around the northwest Himalaya. So and then followed by some major earthquakes. So these big stars basically representing the major earthquake which has been occurred in 2005. This is called Jammu earthquake. In 1905, Kangla earthquake. In 1991 and 1999, Chamoli earthquake and Uttarkashi earthquake. And 1803, so long back, 1803, this is your Chamoli earthquake, but long back. So how do we know about this 1803 earthquake information? Because we were not having the instrument at that time. So this is called not non-instrumental era. So there is a two division, non-instrumental division and instrumental division. So instrumental era started basically since 20th century, and this and then your before that there was a non-instrumental era. And how we study non-instrumental era? Using the paleoseismology. So paleoseismology is one technique and very efficient technique to study such impact of earthquake. So because how we know that, how we locate this earthquake, because based on the impact, you know seismicity, you know magnitude and intensity. So both are very much correlated to each other. One indicate this magnitude relate the release of energy from the focus, and intensity relate the this amount of shaking at especially. So this is how we this so here the amount of shaking we use, and due to this the deformation take place in your geological formations, and based on that we get the epicenter of the past earthquake, which is brought in non-instrumental era. So in space-based, we know that we can use IRNSS, means GNSS. Okay, so in GNSS there are so many navigation constellation, GPS, your GLONASS, Galileo, Beidou, uh, then QZSS, IRNSS is there. So IRNSS and QZSS is these are regional. Okay, sorry, yeah, regional, and rest GPS, GLONASS, Galileo, Beidou, these are global. Okay, and Beidou, some of the satellites of Beidou is regional as well. So when we say regional, means it's only concentrated in the country region only. It's not concentrated to the other parts of the world, and it's only giving the navigation information of the particular region. So this is called regional navigation satellite. So in this image you can see that this is representing the vector, okay, velocity vector. So you can see the all around the world how the velocity vector is distributed, how there you can see the different magnitude, different direction. So it's representing the kinematics of the different plates, starting from the smaller plate to the bigger plate. Okay, so smaller magnitude means movement is small, bigger magnitude means smaller speed is fast. Okay, so you can see this Australian plate, it's having the highest velocity. Then our Indian plate is having 55, 56, and if you go towards north it gradually decreases, and when you enter into Himalaya and you reach to Badrinath, so you get it almost 33, 34 millimeter per year. So you see there are tremendous difference from Bangalore to your Badrinath. So where the rest of the amount is going. So basically it is accommodating. It is accommodating. So how do we know that? How it becomes possible? Because these movement are very, very small. It's in millimeter. All what you see here in this image, these are millimeter movement. So how it become possible? Because we know that GPS it is cannot give this means it gives only the meter accuracy. Our okay. So here in this measurement we require accuracy as well as precision. So how it become possible? So I will discuss and I will try to give you the overview, because in one lecture it is not possible to give everything about the technology, about the application, but I will try to summarize in systematic manner so that you can take in forward manner, and you can, if you have a further interest, you can start the work on it. So you can see here the different constellation and then these are the microwave. So you know microwave, not only the GPS, this SAR also brought a revolution in the microwave technology, and due to this we are able to do the interferometry, because polarimetry is fine, every SAR satellite is doing the polarimetry, but interferometry is something unique mission, so which brought a revolution in the disaster management, because this we require. So because it has it can work in any weather situation. So this is the benefit of this microwave technology. So this GPS and microwave has similar error budget, means they can work in any weather situation, because they are basically operating in microwave region to radar region. So this is the benefit of this mission, to use it efficiently for the disaster management. And this data, it is not only useful for your groundwater measurement, your structure measurement, but it is also possible to see the millimeter change in deformation, either due to crustal deformation or due to aquifer induced, or due to your earthquake. So there are so many volcanism. Okay, so there are so many geological processes which is causing deformation. So you can use these two techniques efficiently to do to measure it in millimeter accuracy. Okay, So there are so many missions, you can see that. So here I will not focus more on microwave, because this lecture will be very in elaborated manner will be taken by our group director. So I will only focus on GPS and other satellites. So you know that in past we were basically using the this cost this where the cost was involved in high, like your Doris, then SLBI, then your VLBI. Okay, so these are the missions which we are doing this plate tectonic moment study, and these are very costly affair. So we want cost effective. So if there is a cost effective, then only this researcher like us, we can use it efficiently and for study this crustal deformation and crustal dynamics in our region. So because in earlier we were using the threadolized based, but it is not so precise in horizontal movement. It was very good in vertical movement. Okay, and this VLBI SLR. So now that's why GPS brought a revolution, and this is cheaper, easier, faster, and doesn't require the sites to be visible from each other. But in the old technique, we require the line of sight, but in the present case we don't require the line of sight. So what we require, minimum 4, and if maximum 4 maximum more than 4 is there, so that is best. So then you can use this technology to study the plate motion, plate boundary deformation, in intraplate deformation, earthquake cycle, then volcanic processes, land deformation, etc. So these are very very critical study, which is now possible with this present technology. So these are the upcoming mission NISAR. So it will be launching, let's see, maybe in this year. So it will be mainly work in L band, so L band and S band. So this will be very very good for deformation studies. So these are the some science questions and science deliverable through NISAR mission. And these are the specification of your GNSS. So you can see that there are huge number of satellites. Huge number of satellites are operational these days. So if you see the NAVIC in another name, it's our Prime Minister has given by, it is given by the Prime Minister, navigation with Indian constellation. So NAVIC, so it is given by Prime Minister. So you can use it apart from INSS also. So then you can see the tremendous satellites are orbiting all around the Earth, starting from 20,000 to 36,000. So these are the range of altitude where the satellites are orbiting, and they are continuously giving this navigation data all around the Earth. So these are using the rubidium clock and cesium clock. These are atomic clock basically. So they are very very precise. So they are having very less impact of these gravitational forces and other this radiation pressure and drag also. So they are having very less impact on them, but still there are some ambiguity, so we have to resolve it. So there are a processing technique which you have to use to do it. This is called the single difference sensing and double difference sensing, by which you can basically remove the ambiguity due to the clock error. So these are the frequencies, L band frequencies and S band frequencies. So S band you get in the NAVIC. Okay, so all the GNSS satellites mainly work in the L band, except NAVIC. These works in S band as well. So there is a reason behind it. So you can see that how globally this crustal deformation and how the population is distributed. Okay, how this major earthquake is taking place, how the your strain budget is distributed all around the world. So in this map you can see that. So if you see it mainly concentrated all along the plate boundaries. So if you see, these are the plate boundaries. Okay, so your strain is concentrated over there. It means strain accumulation is going on. And why strain is accumulating? What is the reason behind it? So you know that our earth is a low pass filter, and then it is our earth is a viscoelastic model. It's like a viscoelastic model, means if you go beyond the crust in the subsurface, you will get mainly the viscosity, high viscosity material. If you come above the crust, above that boundary, so you will get the elastic material. So our crust is a elastic material. So due to the convergence between two plates, so like India and Eurasia both are colliding to each other, and Indian plate is subducting beneath the Eurasian plate. So due to this convergence, and it has a elastic nature, so huge compression is going on, and some part is moving and some part is locked, means it is not moving, it is locked. It's supposed to move actually, and due to the locking, crustal shortening is going on. So continuous crustal shortening is going on, and due to this crustal shortening, huge energy is accumulating over the time, and it will release in the subsequent when it will reach the threshold. So once it will reach the threshold, it will release this elastic energy in the form of earthquake. So this is how your earthquake take place. So what is our job? Our job is to we know that we cannot predict earthquake, but we can give the but we are in this position that we can quantify this energy, that how much energy has been quantified in a particular region. But what we require a past earthquake information. Then only we can quantify in the present. We can give the present situation, that probably how much energy has been quantified in a particular region. So all these thing I will address in the subsequent slide. Because if we have this information, so in some extent we can make this awareness, we can make the preparedness, because these two things can mitigate the future impending earthquake. So here you can see how this technology is doing this modeling and acquiring the data. So you can see the SAR. So this is the co-seismic information. So when we go for any modeling, so we validate this with the co-seismic earthquake. So you can see there are so many co-seismic earthquakes. So you can use any of this earthquake information. So then you can basically constrain your model. So once you constrain this model, you can use it to model it for interseismic deformation. Because interseismic, we don't know how much energy is accumulating, when it's supposed to, when it is going to trigger the earthquake. So we don't know. So for that's why if you want the better model response in interseismic, so you have to constrain with the co-seismic deformation. So this is how you can do it, and you can see the slip model for this earthquake, for this basically the phase diagram. You can see that so many fringes has been developed due to this earthquake, okay, due to the surface deformation. Then you can see in this image that how this crustal strain is distributed due to the movement. Either this is convergent, or your transform fault, or your divergent. So you know divergent, this is having very little impact and producing the damage and this earthquake. But this convergent and transform, they are having more impact and they are producing a bigger earthquake. Because you have seen already in that in case of Turkey, okay, in this Nepal 2015 earthquake, Gorkha earthquake you have seen, then Japan earthquake, okay, Java Sumatra earthquake 2004, 2011 Japan earthquake. So many examples we have seen. So see, convergence is going on here in this region, but you can see that how the crustal strain is distributed. So it has been distributed up to here. So this is just a representation, okay, so graphical but this is not quantified, but you can see if it could be there, and we have seen the response also. If you see the seismicity also, if you plot the seismicity also, you will get the similar concentration, that these energies are getting released in the form of seismicity. But along the plate boundary, there was supposed to be more earthquake, but if there is no more earthquakes, it means plate is locked and it is acquiring the accumulating the strain energy. And you can see here the before the collision of the Indian plate and Eurasian plate. So you can see the Tethys Sea here. So these all are modeled. So based on this ground data and all. And after the convergence, you can see the present status of the Himalaya. So this is the lithology of the Himalaya, and you can see the major structures. Major structures is starting from ITSZ, STD, MCT, MBT, HFT or MFT. Okay, and this is the cross section of the Himalaya. So this you can see, and this is the plate boundary, and this is the plate boundary where the convergence is going on between Eurasian plate and Indian plate. And the rest, this is the different wedges. This is the different wedges of the Himalayan system. Okay, so where the strain is accumulating, and it is not accumulating here, but it is accumulating, most of the energy accumulating here also along the plate boundary, and bigger earthquake basically occurs along the plate boundary. So these are the past earthquake based on the piloseismic study, starting from northeast Himalaya to northwest Himalaya. Okay. So, and you already have got the this reactivation, means recurrence due to this, and this could be maybe due to this post 1500 earthquake, this 2015, but rupture length was very small. So a part of the this 1500, this rupture length has been released, but most of the energy is still there and still in the along the plate boundary, and which is supposed to release in the upcoming year. And this is the surface information about the geology, Lesser Himalaya, Greater Himalaya and basement ridges. So here you can see so many lineaments. You can see the other faults also, like Faridabad Ridge, okay, Delhi Haridwar fault, Delhi Haridwar Ridge, Muradabad fault. So many fault you can see here apart from the major thrust system. And this is how your convergence is going on. So this all become possible due to this GPS only. So GPS is giving this information, and you can see after fixing the Eurasian plate. So this is the moment. So this movement has been evaluated after fixing the Eurasian plate. So that's why you're getting the more velocity here in this system, and less velocity in this region. So wherever you get less velocity, it means the region is under control. It is not moving. It's supposed to move, but it is not moving. So it is locked actually. So this is with respect to your Eurasian plate. And this is the vertical deformation. So in here you can see how vertical fluctuation is there. So vertical deformation having more influence due to the hydrology, but having less influence due to the tectonic. Okay, so tectonic influence is more on the horizontal component, but tectonic influence is less on the vertical component. It is mainly due to the hydrological contributions. So here you can see the vectors all along your Indian region. So this is published by Jade et al. In 2017. So they have used such number of stations to evaluate the Euler pole as well as the ongoing deformations. Okay, so you can see the various researcher has evaluated the Euler pole of the Indian plate, because Indian plate is not having the translation motion, it is having the rotational motion also. So we want the Euler pole, the pole with respect to which this plate is moving in anti-clockwise direction, because Eurasian plate is coming in clockwise direction and Indian plate is going in anti-clockwise direction. So we want the pole of the rotation. So then we can, when we are going for fixing the station to get this relative velocity, so we need this pole information. So if it is more accurate, we can get the more accurate information about the relative displacement. So after getting this better this constant, so it is basically 0.5 million per year is the this angular moment of the Indian plate. So after getting this information, this relative moment has been estimated all along the Himalayan system. So you can see that it is done by Jade et al. Only. and then they estimated the strain. And this is Stevens in 2016. So they have given information about the, they have basically segmented all the fault system and then evaluated the convergence rate, because all this segmented fault having different convergence rate. It is not constant all along the fault system starting from northwest to northeast. So you can see the convergence rate here, it is less, it is 13.3 millimeter per year convergence rate. And if you see here in northeast, it is 21.2 millimeter per year. So it's very high. So if I ask you where the more strain accumulation is going on, if the plate is locked, so it is here, it is in the northeast. So that's why you see more frequent earthquake in the northeast than in the northwest or in the central Himalaya. Okay, and this is the vertical this rate. You can see that vertical upliftment. So it is mainly going on in the higher Himalaya, mainly going in the higher Himalaya. So higher Himalaya is basically uplifting more than as compared to the lower Himalaya and the outer Himalaya. So this is done by the Bilham et al. In 2019, and basically he has given the sleep potentials, how the sleep potential is distributed all along the thrust system in the Himalaya, starting from northwest to northeast. Sleep potential means this sleep supposed to, basically sleeping should be there. So sleeping means this fault should move, actually fault should displace, fault should creep. So this much amount has been this much deficit is there. Okay, you can see the 10 meter, 8 meter, 6 meter, 4 meter deficit is there. So it's supposed to move actually. So, and if it is not moving, so then when mega thrust earthquake will be there, so it's supposed to move, and if it will move the whole amount, then you will get the surface rupture. So if surface rupture is not there, that the fault is called blind fault. So you can see the interseismic movement and then the co-seismic. Then in this Chamoli earthquake, you can see 1991 and 1999. So part of the energy is released, but again the rest of the energy is again stuck. So you can see the interseismic is going from here only. It has not gone here because whole energy is supposed to release. If whole energy is released, then it will next interseismic stage start from the present year. But as the whole energy is not released, so that's why here you can see the break, and another this interseismic started from here only. So this is the qualitative information, but this is the reality actually, what is going beneath the subsurface. And here is the historical information and the sleep release. Okay, and this is the fault, these are the fault length, how much was the fault length in the past earthquake. Okay, so how GPS brought into the picture, and how GPS is giving the millimeter information, because if you ask if any people that how we can get the millimeter accuracy, so they will laugh on you. They may laugh on you. They will say, oh, what are you talking about? It is impossible. But it is possible. It is possible through the PPP. Okay, precise point positioning. So when you are going for this precise point positioning as well as processing, okay, then you have to have this much of error budget, and you have to model the data through making this partial derivatives, so many matrix, okay, linear combinations. Then you should have all this model information, okay, like motion of the satellites, motion of the earth, propagation of the signal. Okay, so there are so many parameters contributing. So these models you should have, and apart from that you should have the propagation information, ionosphere, troposphere. So troposphere having two component, weight component and dry component. And apart from this, you should have the GPS receiver information like clock information, multipath information, antenna phase center variation. Then in GPS satellites, you should have the orbit information, clock information. So once you have all these informations, so you can use this model, you can use this formula, and which is giving the pseudo range, and then followed by the time delay, and then zenith delay, ionospheric delay, and then all this model. So once you subtract this you are getting the frequency. Okay, So when you are subtracting all this information from the raw data, then you will get the true range. And once you get the more than 4 hour beyond true range, then you will get the XYZ precise as well as time precise. Time will be nanosecond, our better resolution. Okay, so this is possible after doing all this modeling and all. So these are the steps of GPS data processing. So you can do it. So, and I already have discussed about this. So here we are basically focusing to study the northwest crustal dynamics. So we have got, Survey of India has launched a mission, and they are basically doing this CORS installation. CORS is nothing but continuously operating reference station. So this is GNSS. Okay, so they are basically doing the setup for whole India. Okay, whole India means including your Andaman Nicobar, okay, all this Ladakh, Jammu Kashmir, your Lakshadweep. So all this region will have huge network. So 1000 plus course network is set up, is going to be done, and almost 1000 station they have already set up, and it is operational. So here presently we are focusing this region to study the crustal dynamics and to do the seismic hazard assessment, that how the fault is distributed, how the fault is behaving, how the crustal budget is going on all along this belt, where the how much strain has been accumulated, how much seismic moment has produced, okay, since 1803, since 2005, since 1905. These are the reference for the past earthquake. So with respect to this different earthquake, how the seismic moment has been stored there. Okay, so we are doing this study, and these are our stations locations and images. So you can see these are the CORS. Okay, so you can see they are continuously installed there, and they are giving 24/7 data. So these are the campaign stations. So when you are going to set up the campaign stations, you have to be extremely careful. If you have done a single error, it will be a garbage. You cannot use this data at all for the crustal studies. So you have to be extremely careful when you are going to do the campaign survey. And these are the continuous operating reference station. This is in Malari, this is in Mohan region, this is in Roorkee, this is in Rajpur. Okay, so these are the ITRF velocity. So when I say ITRF means International Terrestrial Reference Frame. So this is the reference frame which gives the velocity with respect to the center of the earth. Okay, so this velocity giving the absolute information that how the plate is moving actually from the center of the earth. So you can see, so it is gradually decreasing toward your northeast direction. So you can see this is the Dehradun, this is your Badrinath, this is your Kedarnath, Malari, all these Josimath, Karnprayag, all these regions are there. So gradually these velocities are decreasing. So if the velocity is decreasing, it means there is some seriousness. Velocity should not decrease actually, but if it is decreasing, it means there is a problem. It means some phenomena is going on, because if you see the velocity up to Roorkee or up to this Haridwar, so you will get the similar velocity from Bengaluru to Haridwar, because there is very less convergence impact. Convergence impact is almost negligible, insignificant. So that's why you get almost same velocity from your this Bengaluru to your Haridwar, almost maybe 5 millimeter difference or so. But if you go to Badrinath, so here there is a 32 millimeter. So where is the rest of the velocity is going? So basically it is accommodating, and it is basically accumulating in the form of elastic energy. So we have attempted to study the seismic hazard of this region. So you can see the campaign result. So here the R square should be 1, and if you are making the trend line, so this point should be fall on the trend line, and if it is not falling on the trend line, it means you have done an error. Okay, so and R square will not be 1 also. So you can see, so these are representing the displacement. So you can see the displacements are all are optimal and giving the good result for the campaign survey. And this is the continuous information. So this is Pantanagar station, this is Mandal stations. So you can see that the data is not available due to some technical problem, and you can see this continuous displacement, that how due to the convergence how the site is behaving, how the displacement is going on at a particular site. So you can see in the Mandal station, in the Pantanagar station, so this is on the Indo-Gangetic plain, this is on the higher Himalaya. So you can see this, and here you can see this, the velocity is 26. Here you can see the tremendous difference, 35 millimeter. Here you can see 36. Here you get 32. Okay, so these are the things. And as well as you can ask me a question here, almost you get the bigger, because we supposed to get the linear motion, but we are getting some truncation, truncation is there. It is not linear. So what is what is happening there? Because due to tectonic moment, it should have the linear motion. So this is called the non-tectonic contribution. So due to the non-tectonic contribution, this displacement is getting perturbed. So perturbation is taking in the movement due to the hydrological contribution, our non-tectonic contribution. So in non-tectonic, due to the atmosphere, due to the surface hydrology, due to the atmosphere, so many this loading is there, and due to this loading, and your displacement is getting perturbed, and it is mainly happening in the north component. If you see in the east component, it is happening less. It is almost straight line. So it's mainly happening here. So we have to decompose it, we have to separate it. So if you separate the tectonic moment from the non-tectonic, so these are the non-tectonic. So you can see the sinuosity in the non-tectonic contribution. So this sinuosity is nothing but due to the hydrological component, due to the monsoonal. So when there is a monsoon, so peak is more. When there is no monsoon, peak is less. So this is how this variation is there in the north component as well as in the east component. So if you see the amplitude length, our this peak is less. Okay, so and we get maximum in the Mandal. So it means tectonic activity is more in the Mandal than in the Pantanagar. Okay, because Pantanagar in the outer Himalaya. So this is your Dehradun station. So you can see here the linear motion. So this is almost a 10-year data. So here there is your hydrological contribution, but as very long period data. So if you decompose it, then only you can see the your hydrological contribution or non-tectonic contribution. But you can clearly see the hydrological contribution in the vertical fluctuations. So this is the your SAR component, how this SAR line of sight velocity is depicting this particular region. So it is showing that it is having almost a zero trend line, means it's having velocity 0.31 in line of sight direction. So if you see this Mussoorie station, so this is the Mussoorie station. You can see here that it is having data is extremely good here, and then you can see this region is having the very good influence of the hydrology, and not only influence, but it is rising also in some millimeter. So you can see that this movement upliftment is in 4 millimeter per year. So it's on the hard rock actually. This station has been established on the hard rock, and there is no local influence. So it means this 4 millimeter upliftment is there in this Mussoorie region. It means it is rising. So it's a very good study we have done in the Mussoorie region. So this is the spatial location, and not only in GPS station, as well as the SAR, the Sentinel-1A has given very significant information, and you can see the sinuosity also, sinusoidal variation of this region, that the region is going showing the upliftment. So in this line of sight direction, and it is having 1.62 centimeter per year. So value is little bit high, but if we see the trend, this trend and this trend, so both are having the correlation. It means this SARS is also helpful in giving this good information. So you can see the strain budget of these local sites. So you can see the how this cross your compression, extension, shear strain, your this rotation, how these are going on in this region. So you can see here from this result. So this basically region basically experiencing the anti-clockwise motion, and this region is experiencing the clockwise motion. So we have published this in Asian Earth Sciences, and also this region is having experiencing more volume strain as well as this shear strain and then this region. So these all confirmed by these results. And in the regional perspective, we can see the how this compression is behaving. So you can see the how the compression starting from the Indo-Gangetic plain to outer Himalaya to lesser Himalaya to higher Himalaya. So you can see how it is going in direction, and the this compressional strain, this movement is starting decreasing in the south, means IGP, then continuously increasing in the outer Himalaya, then lesser Himalaya, then it is maximum in the higher Himalaya. Okay, so you can see all this behavior. So this is the cross section of the Himalaya. So when we are going to model this GPS data, we need the cross section, or we need the model. Okay, so we have used this model. It is published by Julian Sililier in 2009. So you can see the MHT. This is the plate boundary, main Himalayan thrust. Okay, so we have after modeling. So you can see this is the empty section. So empty section is having also a similar result, and it is correlating with our model data. So you can see the concentration of seismicity. It is falling mainly on the this conductive mid crustal conductor, our this transition boundary. Okay, this most of the seismicity, and this down D part of the MHT is having less seismicity, and up D part is having also the less seismicity. The reason here, it is ductile formation. If you see the rheology, it is ductile formation. That's why you see you get less seismicity here, and you get the sleep rate. So, and as what I have shown the different convergence, so most of the this convergence is mainly taking place and mainly happening along this plane boundary actually. So here it is locked. Okay, and here this the occurrences of the seismicity, there are maximum many region for these occurrences of the seismicity. So after modeling, basically when we are going to model the data, we have to decompose in north parallel and north fault normal and fault normal fault parallel. We have to decompose. So this is the fault normal velocity. So you can clearly see that how this velocity is increasing in the higher Himalaya, and very less velocity in the lesser Himalaya, our outer Himalaya, and it is very much correlating with here also. So after modeling, you can see the result. So here the convergence is going on in this particular region. It is 16.3 hour 7. Okay, and this is the model result. So you can see the observed data and the model data response. So all are having same angle and similar magnitude also, and you can see the this compression also, how the this minimum strain is concentrated all along the model response. So maximum concentration is here only. So here we have attempted this PDF also, probability distribution function. So first we have validated this model with the co-seismic deformation. So after modeling, we have co-seismic, we have taken Morocco earthquake. So after this is the moment magnitude formula. Okay, so after modeling, we got this seismic moment. So this is the MO, this is the seismic moment, and this is the moment magnitude. So this is coming 6.86. So for our model is giving 6.86. Okay, so here actually this we have used USGS also. So it is coming in white direction, white color, so that's why it is not visible. So the response has come good. Just a minute. Yeah. So you can see that this our this particular this GB's model is giving 6.86 model response, and this USGS has published 6.84. So you can see a very good correlation between this two this response. So it means the model is working satisfactorily, and then we have used it for interseismic study. So interseismic, we have taken GPS data and SAR data. Okay, so then after modeling, and we are getting this seismic moment. So this is the seismic moment is for Uttarakhand region. So the 5.16 into 10 to the power 21 Newton meter. So this is the overdue seismic energy in this whole region, whole Uttarakhand region along the plate boundary. And the total energy has been stored, total magnitude is 8.4, and in 8.4, 6.3 and 6.7 energy is released. So if you subtract this energy, so still huge energy is there along the plate boundary, and which will be releasing in the upcoming year. So this is how we have validated, and we have quantified the seismic hazard. So these are the formula. So you can use this GPS to study the co-seismic deformation. So you can see, because when any co-seismic earthquake occur, so either the region go down or goes up. Okay, depends on how the plate rheology, how the dynamics is there. So you can see these stations has experienced that the plate has gone down. Okay, in this case, in this two case, you can see it has gone up. We can mainly see in the vertical deformation. So in the vertical deformation, we can see that it has gone up. So but in horizontal component, all has gone down. Okay, but in vertical component, these two sides has gone up, and this one side has gone down. Means this one side has gone subsided, and this two side has been uplifted. But this relative horizontal movement were all in the down direction only. Means either in the south direction or in the west direction. Okay, so this is about the GRACE. So GRACE is also a very a unique mission, and where it doesn't neither transmit the signal nor receive any signal, but it is giving the excellent information about the hydrology, about the climate change. Okay, so all the hydrological parameter we are getting, and we are giving the very tremendous information with this mission. So I will not discuss more. I will only focus on the results and case studies. So you can see that as I was talking about the hydrological contributions. So if you see in India, in Indian region, in Himalaya, where the most hydrological contribution is going on. So you can see this region is experiencing depletion. Means in the March, April, May month, this your hydrology is very less. Okay, so mass is very less. Okay, so you can see in the negative color it is going down. So this is the anomaly only. But in the this monsoon time, means July, August, September, so you can see it has been increased. Means mass has been increased tremendously. So and then in the post monsoon, again you can see that it is neither it is giving that mass has gone in the negative anomaly or positive anomaly, but it is in the intermediate stage. Okay, so and this is the, and it's supposed to, this region is supposed to get this anomaly in the again. So this is how this phenomena is going on in this three different time period: depletion, enhancement, and the intermediate stage. So this is causing the plate due to this plate movement is getting perturbed, and due to this perturbation of the this plate motion, modulation is taking place in the elastic energy and slip moment. So we have attempted some study, and this is the earthquake cycle. So you must be aware of that, how you can see this is the interseismic stage, this is the co-seismic, and this is the post-seismic relaxation. So if you can see the small interseismic, bigger interseismic, it means it has stored more in elastic energy. it has stored less elastic energy as compared to this time period. So we have attempted this earthquake precursor study also through TEC. So TEC we are mainly doing by the GPS. So in because it is also a very means emerging technique for this getting the seismogenic earthquake seismogenic activity phenomena. So when there is a this seismogenic activity, and when supposed to earthquake is occur, so this they are releasing the positive hold due to the when the rock is getting over stress. So and they are going due to the potential difference, they are going into the ionosphere, and they are depleting the these electrons in the neighboring region, and due to this depletion your GPS velocity is coming faster through that region, and this negative anomaly we are getting more. Okay, so this negative anomaly followed by positive anomaly, when we get such pattern, so then we say that there could be a earthquake. So but we these two patterns should occur simultaneous. So but some author accept this theory, and some author accept only this positive anomaly, though they don't accept negative anomaly. So it depends. So here we accept these two this theory, that negative anomaly followed by positive anomaly. So and we have got so for so many earthquakes, and we have validated also. So this is for Morocco earthquake. So you can clearly see that, and because this your tech variation will be having different magnitude at different station with respect to the epicenter. So you can clearly see this time period. So and this phenomena occurs 15 days 20 days before the occurrences of the earthquake. So here also, so with this you can calculate the epicenter also, but in this case you should have the good array of data, then only you can get the probable epicenter also. So here you can see it is coming 36 kilometer. Okay, so here 36 kilometer, and actually the epicenter is 28 kilometers, so there is a 8 kilometer deficit, but still it's giving the good information that in this region there will be a epicenter. So you can use it to forecast the earthquake, but we need some more this precursor like thermal, VLF, then humidity change. Okay, some more when there, and then radon, then gravity, electromagnetic, resistivity, ground level fluctuation. So many precursors are there. So if we have information from all the precursors, so then we can constrain the knowledge, and then we can do the forecasting in better manner. So this is the 2D distribution of the TEC. So you can see that very close to this negative anomaly is very close to the epicenter. So in other images you don't see such negative anomaly. So it's confirmed that this technique is very helpful in forecasting the earthquake, and one of the precursor technique. So this is another example how you can use this GPS to get this fracture, if there is a fracture development. Okay, so you can see this constant this displacement record is there in the north component, east component, and vertical component. So as you can see here, in this case the movement has taken only in the north component. So that's why you see more offset in the horizontal, this north component, but not in the this east component and vertical component. So this is the Kenya crack development. You might have heard about it. So this is another example of precursors. These are some more example of this kinematic study. So this is the comparison, basically the integrated study for this Nepal and Uttarakhand. And this is another example how this hydrological contribution is there in the Nepal region. This is the seismic microzoation. So this is how you can do the seismic hazard assessment. and it gives the very good information of the impending earthquake. So suppose 7 magnitude, 6 magnitude, 8 magnitude is about to occur, and we don't know how our region will respond. So if you want to know the response, and if you want to determine the amplification, peak ground acceleration, peak ground displacement, our velocity, then you have to have this study, seismic microgeneration. So based on that, you can do you can get the information about the all these parameters, and then accordingly you can plan the this building design, construction, civil construction, and preparedness, awareness. All this you can do it in better manner. And this is the active faults in Dehradun region. So when you are going to do this active fault mapping, so you know there are some criteria for the active fault study. So some of them like elevation change, sudden elevation change, your lithology change, scarp development. So if you are getting such information, okay, in any region, so it means there could be a fault. And then once you get this surface feature, surface change, our anomaly, then you go for the trenching, and then you can confirm the fault, you can date the fault, and then you can give the information about the paleoseismology. So this is about the how geophysics, how ground-based technique is useful to get to detect the this active deformation like HFT. So you can see the trenching result. So this is the 3 generation of fault here. You can see clearly, and we have done this ERT, MSW, GPR across the your this HFT across this fault to get these features. So you can see in these 3 technique, you can see the response. So clearly you can see the this due to this lithology change, because this your tertiary is having the mainly the your sandstone conglomerate, all these formations they have mainly the sandstone, because middle Shivalik you get in the here, and this quaternary is having mainly the alluviums. So you can see this is the alluvium, okay, and these whole are the your tertiary formations, and you can see the this truncation and the sharp contrast in the resistivity. So clearly it is detecting the sharp contrast in the resistivity that the fault, this its thickness means fault zone, that you know fault is not a line, it's not a single plane, it's having the zone. So you can clearly see that some zone is there, so you can clearly see, and sudden change. So if you get such contrast in the resistivity in your section, so it means there could be a fault, discontinuity, lineament, fracture, it could be there. So if you know the geology of the region, accordingly you can interpret. And this here you can see the low velocity zone, our velocity variation. So you can see the velocity is going down, and it is dipping in the northeast direction only. So clearly confirm the presence of fault in this more special this GPR and then less special this GPR geophone distribution. And in GPR as well, here you can see the offset, you can see the truncation, you can see the displacement in the GPR. So in 3 type of frequency, you can clearly see the presence of fault. Okay, so because GPR detect many minor displacement, our fracture, our truncation, our offset, if there, it can detect all those things, because GPR is very excellent and very powerful tool to do for the structural characterization, our structural delineation. And this is how you can use this 3D. So here in upcoming this is our way forward, that we are going to use this 3D GPR now for this various studies, paleochannel studies, your active tectonic studies, fault mapping, subsidence. So for various study, we are going to do this 3D mapping. So this is how we will do, and we will quantify, we will make the cube, and you can see the lateral variation, vertical variation. So you can see all the variation in the 3D. So this is how we have planned in the near future. Thank you very much. And this is your rupture You can see the rupture of 1934 earthquake. So if you get such rupture, it means whole energy has been released. Now the civilization is safe for the maybe next 500 years, 400 years or so. So if you get such rupture, so then it means whole energy is released. So there is no more blind fault.